Chapter 1 of the Reinforcement Learning book by Sutton and Barto introduces reinforcement learning, a third paradigm of machine learning. There are three paradigms of machine learning: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning trains from labeled examples provided by a supervisor. Unsupervised learning finds hidden structure in unlabeled data. Reinforcement learning learns from evaluative feedback through direct interaction. Unlike the other two, reinforcement learning is especially suited to interactive problems where an agent must learn from its own experience through trial and error. A reinforcement learning agent is a goal-directed agent that learns by interacting with an uncertain environment. It senses the state of its environment and has goals relating to that state. At each time step, the agent senses the state of the environment and selects an action to perform on the environment. The action causes the environment to respond with a reward signal and may result in a transition to a new state. The agent uses the reward signal to learn over time, a policy that is a mapping from state space to action space such that it maximizes the cumulative reward. This cycle of state, action and reward is the fundamental interaction loop of reinforcement learning. Trial and error search is the first distinguishing feature of reinforcement learning. The agent must explore different actions to discover which ones lead to high rewards. There is no supervisor to tell it the correct action. Delayed reward is the second distinguishing feature. Consequences of an action may not be felt until many time steps later, making it challenging to determine which past action was responsible for the reward. A policy defines the agent's behavior. It is a mapping from states of the environment to the actions to be taken when in those states. The policy is the core of what the agent learns. The reward signal defines the goal. The environment sends an immediate reward to the agent at each time step, and it is the primary basis for altering the policy. The value function specifies what is good in the long run. The value of a state is the total future reward an agent can expect to accumulate starting from that state. Values are predictions of long-term reward, not immediate reward. A model of the environment mimics its behavior. Given a state and action, it predicts the next state and reward, enabling planning. Methods using models are model-based. Those without are model-free. A fundamental challenge in reinforcement learning is the trade-off between exploration and exploitation. Exploitation means choosing the greedy action with the highest estimated value. Exploration means trying a non-greedy action to discover potentially better options. The agent must balance both. It cannot always exploit because it may miss better strategies, and it cannot always explore because the goal is to maximize actual cumulative reward. Consider playing tic-tac-toe as player X against an imperfect opponent O. The state is the current board configuration of X's and O's. The value function is the probability of winning from a state. States where player X has won are assigned a value of 1. States where player O has won are assigned a value 0. All other states are assigned an initial value 0.5, which is updated as we play many games. By playing many games, we record the states that were traversed and the result of each game, which is victory or defeat. Then, we update the value estimate of all traversed states as the fraction of wins from that state. Most moves are greedy, choosing the action leading to the highest valued state, while occasional exploratory moves help discover better strategies. Temporal difference learning updates the value function after every greedy move. V of ST is updated by adding alpha, the step size, times the TD error, which is the difference between the value of the next state and the current state. Unlike a simple end-of-game update, temporal difference learning updates after every greedy move. Successive estimate differences drive learning, bridging trial and error search with dynamic programming. The history of reinforcement learning has three distinct threads of research. Trial and error learning originated in animal psychology in the 1800s with Thorndike's law of effect. Optimal control was formalized by Bellman's Markov decision processes in 1957 using dynamic programming. Temporal difference learning is driven by differences between successive estimates of the same quantity. All three threads converged in the 1980s. Their convergence gave rise to modern reinforcement learning with landmark contributions from Ian Witten in 1977, Richard Sutton in 1988, and Chris Watkins in 1989.